Okay, 1.3. Okay, conditional statements. Okay, the conditional operator okay, is used, okay, that's the operator is an arrow, is used to create conditional statements. The P arrow Q, okay, is a conditional statement read as if P, then Q. Okay, if P, then Q. Where P is called the hypothesis and Q is called the conclusion. Okay, this is sometimes also expressed as P is sufficient for Q, or P implies Q. Okay, so let's look at the truth table for if P is true, then is Q true? And what happens if P is false? Then is Q false? Or could they be, yeah, let's figure this out. Okay, we have P, Q, and then P implies Q happens. Okay. So for P, we're going to have true, true, false, false. For Q, we're going to alternate true, false, true, false. Okay, so we only have four rows because we have two variables. Okay, two propositions. Okay, connected by the operator. Okay, which makes it the conditional operator, which makes the conditional statement. Okay, P implies Q, or P is sufficient for Q, or if P, then Q. Okay, so if P is true, then Q is true. Is that a true statement? If P is true, then Q is true. That would be true, right? If P is true and Q is true, then P implies Q. Okay. So true. Okay. Does P imply Q? If P, then Q. So we're creating a logical statement here. So think of it more like if it rains, then I carry an umbrella. If it rains, then I carry an umbrella. Okay, so if the statement it rains is true, and the carrying of the umbrella is true, then the statement, if it rains, then I carry my umbrella, that's true. Okay. We could say P is rains, and then Q is umbrella. Okay, if it rains, then I carry my umbrella. Okay. Okay. What about T implies false? Okay. Does the rains, okay, if it rains, okay, am I gonna have an umbrella or not? Well, I'm gonna have an umbrella. If it rains, I'm gonna have an umbrella. So what happens if that proposition is false? Well, then it breaks the logic. The logic is broken. Okay, then that's not, then the implies, P implies Q is not true. It breaks the logic there. Okay, and so T implies F. No, a true statement implies a true statement. Then the logic holds. Okay, this logic holds. This logic breaks. Okay, then raining and umbrella are no longer linked. If I'm not carrying my umbrella and it's raining, then you cannot say logically that if it rains, I carry my umbrella, because I have shown you to be a liar. Okay, the logic has broken. Okay, but what if it doesn't rain? What then?
Then you don't carry the umbrella?
No,
You're still gonna carry the umbrella.
no. It doesn't matter. If it doesn't rain, if the hypothesis is false, then it doesn't matter whether or not I carry an umbrella. Because the condition is that it rains. I could carry an umbrella on a sunny day or not on a sunny day. It doesn't really matter, because it has nothing to do with the premise. And so if the hypothesis is false, then the implies is actually always true. I could be true if I carry an umbrella, and I could be true if I don't carry an umbrella, because it doesn't matter. Because the hypothesis, the one that Q depends on, is broken. Okay. So if it is sunny, I could carry an umbrella, I could not carry an umbrella. It doesn't matter. And so the truth value of that statement is true regardless. If your hypothesis is false, you can have any statement you want, and it would be true. I could carry an umbrella, true. I could not carry an umbrella, true. Okay.
Excuse me, I have a question. So is it fair to say that, like, if P is false, It's like the two things aren't connected.
They are still connected. It's the truth values that we want. We want to know, can we logically conclude on a sunny day whether or not I walk outside with an umbrella?
Okay, thanks.
Does that make sense?
Yeah.
Okay. So you want to draw a logical conclusion between your hypothesis and your conclusion, right? You want to say, okay. Okay, and we can do that with something else. We could say, if I'm in the water, I'm wearing my bathing suit. If I'm in the water, I'm wearing my bathing suit. Professor Holtman's in the water, he's got his bathing suit on. Okay? In the water, bathing suit. I shower and bathe in my bathing suit. Okay? But what happens if I'm not in water? Could I still have my bathing suit on?
Yeah, it doesn't matter, so it'll be true regardless.
Exactly. Exactly. Okay. Let's do another example. If you mow Mr. Smith's lawn, and this example comes right out of the book, then he will pay you. Okay. So P, if P, then Q. Okay, if P, then Q. P implies Q. Okay. Okay. So if I mow Mr. Smith's lawn, I forgot the word lawn, sorry. Then he will pay. If P, then Q. Okay. So if these are both true, then it's a true conditional statement. True, true. Okay. So let's rephrase this a little bit. Okay, if you mow Mr. Smith's lawn, then he does not pay you. Is that logically correct? No, because we already established that the above is a true statement. So this one must be a false statement. If you mow Mr. Smith's lawn and then he will pay you, and we assume that that's true, that that's the initial hypothesis and conclusion. Then if you say, oh, if you mow Mr. Smith's lawn and then he does not pay you, that's a false statement. Why? Because we would assume this to be true, and then this to be false, and T implies F is always a false statement. No, Andrew, you want to look at both, okay? Because the only time that you get a false conclusion is when you have this happening here. Is when your hypothesis is true and your conclusion is false. That's the only time out of the four where you end up with a false conclusion. Okay. Okay, what happens if you don't mow Mr. Smith's lawn?
It'll be true regardless,
Yeah, why?
because the initial hypothesis is incorrect. So the conclusion doesn't really matter.
Give me an example in this scenario. If I don't mow Mr. Smith's lawn, then he pays me. Why is that a true statement?
Because you still get paid.
No, because I could have done something else for him and he could have paid me. Does that make sense? He could have just paid me out of the generosity of his heart for doing nothing but ringing his doorbell. The paying is conditioned to the work. If I do the lawn, he pays me. True. If I do the lawn and he doesn't pay me, false. If I don't do the lawn, he could still pay me. There's no break in logic there. He could pay me for something else. It doesn't matter. F implies true. Okay, sure. The hypothesis is creating the base for which your logic is dependent, and then out of that is birthed the conclusion. You cannot birth the conclusion out of a false statement and have that, be some sort of one-to-one logical statement. It's true regardless, right? Because again, he could pay me even if I didn't do anything for him. But if I mow his lawn, then he pays me. Okay. Okay. If you do not mow his lawn, then he does not pay you. Well, you probably think, well, obviously. Okay, obviously, if I don't mow the lawn, there's no premise for payment. The only time you have a premise for payment is if your hypothesis is true. And if you break the contract, then it's false. That make sense? Okay, P implies Q is what we call unidirectional. It's one way. Okay, P implies Q, and Q does not imply P. Okay, if P, then Q must follow. Okay, and this is not true in reverse order. Okay. Well, it could, I don't want to put a true statement. It's just not, we'll just say not in reverse order. Because it depends on the scenario for the truth statements. Okay. Okay, but P implies Q is not the same as Q implies P. There should actually be 3 here. We'll get to what that means in a little bit, why there's 3 and not 2. Okay. Okay, proposition. Okay, is if P, then Q. P implies Q. Okay, what we call Q implying P, we call that the converse. That's if Q, then P. So Q implies P. Okay, that's the converse. And the proposition, the converse, they are not the same. The inverse is when we negate the proposition in that order. If not P, then not Q. Not P, not Q. And the contrapositive is if not Q, then not P. Not Q implies not P. And the original proposition and the contrapositive will have the same truth value. So it will have the exact same truth table. The contrapositive is logically equivalent the three equal sign with 3 dashes means logically equivalent. Okay, is logically equivalent to not Q implies not P. Okay, the truth value. Okay, the truth value of the original proposition and the contrapositive will always be equal. Okay. Okay. If it rains, then the game is canceled. We'll just say that's the original proposition and it's true. Okay, if it rains, then the game is canceled. True. Okay, what's the logical equivalent to that for the contrapositive? If it, what? Let's help me write the contrapositive here. If it, this is not Q implies not P. If the game is not canceled, then what?
Then it didn't rain.
Yeah, exactly. Thank you, Michaela. Okay, then it did not rain. Right? Does that make sense? If it rains, no game. But if the game goes on, then what do we know? It could not have rained. Okay, then this is true. Okay. Now we just stated that the original condition and the condition where we have P implies Q and Q implies P, they're not the same. Okay, those conditional statements. However, there is a case when they are the same, when P implies Q and Q implies P, where they are logically identical. And that is called a biconditional statement. Okay, so P, if and only if Q. P, if and only if Q means denoted as P, and now we have a double arrow, which means that it goes both ways. P implies Q, Q implies P, both ways. Is true when P and Q have the same truth values. And is false when they do not. Okay, so let's write the P implies Q. P, Q, and P, sorry, P if and only if Q. Biconditional statement means that it's only true if P and Q are identical. If P is true and Q is true, then P implies, or P if and only if Q is true. True statement. Okay. Okay. So if P then Q is false, then this thing breaks down. They're not identical. Okay, then this is false. And P implies Q would be false. Q implies P would be true, but the combination of the two is false. Okay. False and true. Okay, that's again false. Okay. True, because Q implying P would give me a false result. It doesn't matter that a false implies true gives me a true result. It's the fact that it's an and statement. They've got to both be true, or they have to both be false. Okay, false implies false. That is actually true. They're identical then. Okay, P implies Q, false implies false, true. False implies false, true. P goes to Q, true statement. Q goes to P, true statement. They're both true, true. The term if and only if, or IFF, is used as an abbreviation for if and only. Okay, if and only if. Okay, so P if and only if Q, okay, is equivalent to P if and only if Q. Okay, a biconditional statement is the same for the conditional P implies Q and its converse. Q implies P. Example. Okay. Okay. a polygon is a triangle if and only if it has three sides. Okay, that's a true statement. Okay, the if and only if means that these are equivalent statements. A polygon is a triangle is identical they're identical statements. They're identical to a figure with three sides is a triangle. It's the same thing. Okay, one is the other, and the other is the thing. Basically, when we start talking about definitions, a definition is itself. It's what is being defined. Okay, if we define a triangle as a three-sided figure, then the triangle is a polygon with three sides. And a polygon with three sides is a triangle. It is the same thing, identical statements. Okay. If we wanted to break this up into its two statements, going forwards and backwards, in English, we wanted to write the original. This is a biconditional statement. If we wanted to write the English, P implies Q, what would we do? We would say, if a polygon is a triangle, then it has three sides. That's the easy way. Let's go backwards. P implies Q. If a polygon has three sides, then it is a triangle. Okay, forwards, it's true forwards and backwards. Okay. Back to order of operations. Okay, 1 was not, 2 was and, 3 was or, and 4 is okay, our conditional statement. Okay, and then 5 is our biconditional statements. Okay, so order of operations. Okay, unless there's parentheses. Oh, sorry. Or is that? Okay. Not, and, or, if, then, if and only if. Okay, those are their English equivalents. Okay, let's do an example. So, example 2. Okay, P is true, Q is true, and R is false. Okay, P is true, Q is true, R is false. Okay. So P and not Q biconditional with R. Okay. So we're not creating a truth table here. We just want one line in the truth table. We want one line in the truth table. That's the TTF line in the truth table. So we want true or not, okay, true implies false. Right? Is the biconditional a true statement?
No.
What? Eric, I didn't hear that.
It's false.
All right, maybe I need to turn my volume up.
It's false.
Yes, it is false. Okay, it is a false statement. Okay, because for a biconditional, they either have to be both true or both false in order for them to be identical. So this is false. Okay, so we do the not now. So what's the not of an F? That's true. Okay, thank you, Lauren. Okay, and true or true, well, that's an easy one. It's true. Right? So that's T. You can leave it as T or true. It doesn't matter either way. Okay. Okay, does anybody have any questions on anything?